So in this lecture, we're going to do something a little different. The proof is still going to have a real algebraic kind of feel to it, but instead of doing something that's purely algebraic, like a formula or an inequality, we're going to look at a result from number theory. Right? We're going to show that we can use this idea of induction to prove things about divisibility. Right? For example, right, we're going to show here that 3 divides n cubed minus n for every positive integer. All right, so first we need to look at our basis step, right? So we're talking positive integers. Does that include 0? Or, well, it works for 0. All right, so let's start there. Right, so let's say if n equals 0, then n cubed minus n equals 0, and 3 divides 0. Good. So we're squared away, and you can try it with 1 as well. Right? If you put 1 in there for n, you also get 0. So it works for that value also. So now we need to move on to the inductive step, right? So what do we need to do? We need to show that if 3 divides, sorry, got a little sloppy there. If 3 divides n cubed minus n, then 3 divides, and we need to do it with n plus 1, right? So it'll be n plus 1 cubed minus n plus 1. All right, so let's look at that, right? Let's look at that expression. N plus 1 cubed minus n plus 1. And I'm going to simplify this, right? I'm going to multiply it out. Right? If I multiply out that cubic part in the front, it becomes n cubed plus 3n plus 3n plus 1 minus n minus 1. And I'm kind of feeling good about that. I'm trying to show divisibility by 3, and I'm seeing some 3's in there, so okay. Now at this point, kind of the natural thing to do, something your algebra instincts are probably telling you to do, is to combine the 3n and the minus n. But that is actually not what I'm going to do, because again, right, I like that 3. I like having that 3 there. And if you look back at the inductive hypothesis, there's a minus n in there. So I actually would kind of like for there to be a minus n in my expression. So here's what I'm going to do. I'm going to rearrange this. I'm going to bring the minus n up to the front. N cubed almost to the front. N cubed minus n plus 3n plus 3n. And, excuse me, that should be a 3n squared there, shouldn't it? 3n squared. And I am going to combine the 1 and the minus 1 and let them cancel. Okay, this is what I need. I'm going to do one more thing. I'm going to factor out the 3. This is n cubed minus n plus 3 times n squared plus n, and that's what I needed. All right, that did it. This part is divisible by 3 by the induction hypothesis, right? That's where we started. This part is also divisible by 3 by definition, right? It's got that 3 out in front. It's 3 times an integer. Well, if the individual parts are divisible by 3, then the whole is divisible by 3. So therefore, 3 divides n plus 1 cubed minus n plus 1, which is what we needed to show. Right? And again, just like we've done in the previous examples, let's break this down a little bit. Right? We showed the base step here, and then everything from here down was the inductive step, and this part here specifically, that was our inductive hypothesis, and we did use that right here in the body of that part of the proof. So hopefully you're beginning to see kind of the variety of things that we can do with this mathematical induction approach. We've seen some algebraic results. We've seen a result here from number theory. In the next lecture, it's the last one in our series of examples, we're going to do something entirely different. Right? We're going to go in a completely different direction and see how you can use this induction technique to prove a geometric theorem.